All right.
There you go, Michael.
Okay, great. All right, thanks everyone for having me. So today we're going to be looking at kind of a nice combinatorial problem involving trying to construct a fair game using an unfair coin. So let's look at the game first. So our game is, suppose you and your three very best friends have a coin with probability of heads p, right? If you flip this coin n times, there's 2 to the n possibilities, right? So we're viewing heads, tails as being different from tails, heads. So you do with each of these possible outcomes, you put them into one of 4 groups, and for each group, you assign that to some person. And if the actual probability, so when you actually flip the coin, whoever's assigned probability matches the actual probability is declared the winner. So this is the game. Of course, what's the problem? Well, the problem is, for what values of p can you construct a fair game? In other words, for what values of p can you make sure that it's an equal chance of each person winning, right? So nobody feels like they're being left out. So maybe what we call the trivial solution, or the not so interesting solution, is probability of 1/2, right? If you have like a normal coin, then certainly flipping it twice gives you heads, heads, tails, heads, heads, tails, and tails, tails, each one with equal probability. You assign 1 to each person, and that's certainly a fair game. Of course, this is not interesting at all. So the real question is, what other probabilities work, right? So for an unfair coin, what will work? And so before I just sort of produce a probability, right? Maybe you'd guess like 1/3, 1/5, or something like that. But before I tell you what that is, so you'll try to construct it. So let's just suppose you flip it 6 times. I'll explain why 6 in a little bit. So if you flip it 6 times, this means you have an equation that looks like this, where Q is the probability of tails coming up. All right, you can expand this thing, right? So just multiply it out. And so each term represents a possible outcome, right? Counting or not counting multiplicity. And so what the idea is if we try to take as many terms divisible by 3 as possible, leave them off to the side like this. So we have all of our terms, as many terms as we can find that are divisible by 3, put them off to one side, all right? And just leave the leftover terms over here. And so now what the idea is, for all of these terms, right, this set of terms occurs exactly 3 times. So for each of your friends, you can assign them that set of outcomes. So at the very least, all your friends have an equal chance of winning. And so all that's left to do is to make sure that the leftover is equal to what each of your friends get. So in other words, what you get is equal to everyone else gets. But another way of saying this is that, right, what you get is the probability of 1/4. And now you can kind of see why flipping it 6 times works so nicely, because what we have on the right-hand side here is a perfect square. And this is something that we should be able to solve without too much trouble. And indeed, if you shift your variables a little bit, right? If you let r or p equal to 1/2 minus r, you're able to solve this with very little difficulty. So you obtain a probability of 1/2 minus 1 over root 12. And this is kind of surprising. At least I don't think it'd be your first guess if you wanted to guess a probability. So I guess the main question now is, why does this work, and can we reproduce it? So why it works? Well, we're talking about binomial coefficients, so it's probably very natural to think about Pascal's triangle. So, what's special about flipping it 6 times? So let's look at Pascal's triangle. Right, if we look at the bottom row, or the 6th row, this is really the coefficients we got when we multiplied out that, p plus q to the 6. And so what we did is, if we kind of in some sense, you subtract rows from Pascal's triangle to obtain things only divisible by 3. So if you think of subtracting the 6th row from the 2nd, right, 1 minus 1 is 0. That's congruent to 0 mod 3. 6, 15 are already congruent to 0 mod 3. 20 minus 2 is 18, which is divisible by 3, and et cetera, right? So using this idea of if we have a larger row of Pascal's triangle minus a smaller row to give you everything congruent to 0 mod 3, then this should hopefully produce a solution. And so I guess the next question is, can this strategy ever work again? Well, of course it can, otherwise I wouldn't be talking about it. And indeed, if you flip it 9 times, you look at a few more rows of Pascal's triangle. And in this case, if you take the 9th row, right, minus the 3rd row, you get everything divisible by 3. right? So you subtract it in this way, everything is divisible by 3. And so hopefully we would expect this to produce a solution. And indeed we do, right? Again, not something you might guess, but you obtain a probability of 1/2 minus, right, this, this horrible looking thing. And so so this is certainly the story for 3 people, but I think there's lots of unexplored areas that we can go as well. You can look for maybe 3 people, 5 people, etc. But I think that's all I have to talk about. So thank you very much.